All right, here we go. Talking about 12.1, and this is test on regression. And what we're really looking for a test on regression or confidence interval on regression, we are focused on the slope. Okay, so let's go through some problems and let's see what it looks like. College teacher asked random sample of 10 of the 250 students in her introductory statistics class to record the total amount of time they spent studying for a particular test and then combine these times with the student's score on the test. She then performed regression analysis. Below is the numerical and graphical output from her software. Okay, so first thing we got to be able to do is read one of these graphs, right? Very, very important. The word constant, we talked about this back in the first semester. That is your y-intercept. The descriptive word, in this case, study time, is the slope of the equation. So if I just needed to, and they might ask this question in a second, but I'm jumping the gun a little bit. I know that I could go y hat equals 62.100, that is the y-intercept, plus 12.00x. This is the generic least squares regression line, that would get pumped right into this data set. And it's coming right from these two numbers there. So the coefficient is the big thing to look at here. All right. So let's look at some other stuff that I'm seeing right now as I look at this graph. It's looking very much linear. So I like that it is linear. It's definitely in a positive direction, right? It's moving. So from the left to the right, it looks like it's moving up or positively in there. Let's take a look at the residual plot. Residual plot, we're looking for no pattern. To confirm, do we have a linear data set, right? No pattern is good for linear data set. So you're going to have to debate this with me because somebody might say, you know what, it looks like it definitely has a pattern. And others might say, you know what, this looks like a pretty random scattering. I don't see a pattern. So no pattern is good on that one, right? So just looking at a residual plot, that's what it tells me. Is a least squares regression line a good fit for this data set? So notice it is a residual graph because it says residual on the side. Okay, let's look at an NPP, normal probability plot. In order for data to be normal, a normal probability plot, we want to see a straight line going from corner to corner. This is pretty straight here, right? If you see it highly curved, we're going to say not normal. But this case, we would say the residuals are fairly normal in their pattern because of the straightness of the line from bottom to the top. All right, think about just drawing a line and do they kind of like follow that line or not? Right, so that's what a normal probability plot. Okay, so here we go. Do these data provide convincing evidence of a linear relationship between time spent studying, perform the appropriate tests of significance to support your conclusion? So when we are asking for a linear relationship, I need the slope to not be 0. That's it. And if they said a positive linear relationship, I want the slope to be greater than 0. If it's a negative, I want it to be less than 0. All right, so let's dial in this convincing evidence. That is a phantoms problem. Okay, so H, what is my null hypothesis? Null hypothesis, always going to be beta, the true slope of the entire population, is equal to 0. We're always going to assume there is no linear relationship. And alternatively, that's what we suspect or hope to see. We want to see is beta not equal to 0. Right, so it looks something like that. Okay, assumptions. Remember, there are 5 assumptions on this one. 1, 2, 3. But 1, 2, 3 is all about the shape, and then you get 4 and 5. So usually it's just, right, is it random? And then the 10% rule type idea. So I'm going to go ahead and do that, right? They said random sample of 10 and 10% rule. They said there's 250. So first of all, yes, it's a random sample. Second of all, is 250, that's the entire class size, greater than or equal to 10 times my sample size of 10. So greater than or equal to 100? Yeah, it is. So that's pretty much checked out. Okay, so then what are the things we're checking for? We want to make sure my data set is linear. We want to make sure that it's got equal variance. And we want to make sure that the residuals are normal. Right? So that's what we're after here. Okay, is it linear? I can really, again, go to this, no pattern in the residual plot. That confirms that it's linear enough for me to use. So I'm literally going to write here, no pattern in residual plot. So you want to talk about what it is that you're looking at. Awesome. Equal variance. Again, go to the residual plot. Doesn't look like it's equally spaced above and below and randomly scattered, right? Or is it more weighted on one side or the other? This looks good enough. Like I can't argue against it, right? Equal variance. So we're just going to call it equal space on residual plot. So really no tree shape. Remember I showed like in the video, like here would be an unequal variance is if it started real small and then it started in it. It's what we call like looking like a tree that's on its side, right? I mean, right? If I had dots that look like this, that kind of looks like a tree laying on its side. See, that would be bad. That would be unequal variance. But this here, I'm okay with it. Okay, so what's next? Residuals are normal. That's why they gave me the normal probability plot of the residuals. And again, since they are moving in a straight line from corner to corner, we're going to say NPP is straight. That's good enough. That will tell you yes. Okay, there is my shape check, right? Unfortunately, on this one, your shape check consists of 3 units. So that's what it would look like there. Okay, let's keep moving. T is actually doing the test calculation. So we are all about the slope right now, and so we know that the slopes always produce a t-test. So we're going to draw a t-curve. So we're going back to this idea of a t-test, but now for slope. Where are we going to center this at? At 0, because that is the claim right now, right? So that's what that looks like. And then what we have t equals, and we could do the whole t calculation, but let's just get right to it, especially if you're doing the AP. Check this out. So remember that the descriptive word represents slope, so everything in this row represents the slope. So the t value against the slope is 4.25. So let's just do that. So we got 4.25. That is my t value. Now, what is the degree of freedom? Just in case we need to know, it's n minus 2 because we're bivariant data, right? Bivariant data means we need to subtract 2 from the sample size, not 1. In a typical t-test, we usually subtract 1. In this case, we subtract 2, so it's 10 minus 2, so it's 8. If I need to know the degree of freedom, it's 8. Let's obtain a p-value. So p-value is roughly equal to, well, guess what? Let's go back to this computer printout right here. The slope is study time. There's the p-value right there, 0.003. So let's put that on here, 0.003. Now, let's mark that on our graph. So t is 4.25. So imagine 4.25 standard deviations. I would mark my t. I would shade a little bit. But what does this tell me? Shade the other side too. Oh, we got to shade both sides. Okay, so there it is. I didn't have to really do a whole lot of work. I just know how far I am supposed to be from the middle, and I know I should be shading both sides. Let's make a decision. Such a small p-value, let's go ahead and reject at alpha equals 0.01. Let's just I'm going to use the small. So summary, we have evidence to suggest, a linear relationship between time spent studying and test score. Okay, so there you go. All right, phantoms, all based on the same thing. All right, so let's do construct and interpret 95% confidence interval for the slope of the population regression line for the predicting test score from study time. So here's what we're not going to do. We're not going to do this part again, But when they ask for a confidence interval, I want you to think panic. But let's just do the interval setup in calculation. Okay, what does the normal interval setup look like? It is going to be, it's going to be b, the slope of the sample, plus or minus t star times standard error of b. That's literally it, right? So let's go plug in the right values. So let's go back to this. What is the actual slope value? It's 12. Okay, so that's going to be the first number we're going to plug in. So we got 12 plus or minus t star. Let me come back to that in just a second. But let's do standard error of b. What is the standard error of b? That is in our computer printout again. SE coefficient, if the coefficient is the slope, the standard error of the slope is that one, 2.825. So here we go, 2.825. And then T star. This is always a lookup on the T table. So let's jump to the T table here. Okay, here we go. So what are we talking about on the T table? We need to find degree of freedom. We already established that it is 8. That's 10 minus 2. And then I need to slide across until I am above, what is it, 95%. Sorry, I had to switch back there. 95%. So where do those two come together? 2.306. 2.306. That's what we're going to write in here. 2.306. Now we are ready to give the confidence interval. Notice I did not have to do anything there so far except for kind of just figure out those different pieces on that. All right, so I'm grabbing my calculator now, and now I'm literally just going to physically type this in. Unfortunately, there's not like a great little function. There is a regression test for regression in your calculator, but it needs actual data in order to use it. Since most of the time we don't get actual data and then we only get computer printout, we have to use this. So I'm going to go 12 plus parentheses 2.306 parentheses 2.825. Let me do that again, 825. Okay, so here's what I get on my upper end, 18.51445. Why do I get that as my upper end? Because I use the plus. So I'm going to go second entry, and I'm going to change to a minus sign. And I get 5.48555. That's it. There we are. That's the interval calculation. Let's do the conclusion. Well, now we know conclusions on these by now, right? We are 95% confident the true slope between time studying and exam score is captured in 5.5 to 18.5. So just change up the wording a little bit, but the same thing. We're 95% confident that this interval captures the true slope between studying time and exam score. And we got it. Okay, that's it right there. There is the overall. That is phantoms and panic together. All right, let's try another one right here. Psychologist counsels people who are getting divorced, suspects it is possible to predict among couples he works how long a marriage will last from how long the divorcing couple's courtship was before they got married. Courtship is just kind of that, like, I am dating, but I am dating with the purpose of possibly marrying, right? That's what courtship means. So he selects a random sample of 10 of hundreds of couples from whom he has records and performs a regression analysis. Below is a numerical graphical output. Okay, so here we go again. We have to be able to read output. That's going to be our number one goal in chapter 12, read output. So I'm reading output, I'm looking at all this, and then I'm going to answer some questions. Here's the actual scatter plot, here's the residual plot, and then here's the normal probability plot. Well, they're giving me everything I need in order to do the assessment. Do the data provide convincing evidence? Provide convincing evidence that there is a linear relationship. A linear relationship. Do we care if it's positive or negative? No, a linear relationship. So let's do it. Oops, I should do this. Null hypothesis. beta, the true population slope, is equal to 0, always the standard. And then we're going to say beta, in this case, not equal to 0. We don't care if it's positive or negative linear relationship. We just want to know that there is a relationship. All right, assumptions. Remember, there are 3 of them that consist of the shape, and then you got random, and you got 10% rule. So yes, it did say random sample of 10 of hundreds, right? So all, what are we talking about here? Let me just say hundreds of couples for whom he has records. All couples in his records, is it greater than or equal to 100? Well, it says hundreds. So yeah, I believe he's got more than 100. All right, let's do this real quick. Let's tack on, is it linear? Well, residual plot, no pattern. So linear, residual plot shows no pattern. Good. Equal variance. Again, equally spread throughout. And then finally, does the NPP show a straight line? Yes, right? I mean, for the most part, it's more straight than not straight, right? They're kind of moving from corner to corner in a straight line. So, okay, everything checks out there, right? Boom, boom. So we are good to go. Let's start the calculations. We know it's a t-distribution. We know it's centered around 0. That's always going to be the case here, right? My t equals, we don't even have to show the formula on the t really to get that stats credit, but here we go. Courtship, so there's the actual slope, there's the standard error slope, there's the t, there's the p-value. We're looking for the t right now, 3.68. So 3.68, we know that because the alternative is not equal to, we're going to go to this side, shade a little bit, we're going to go to this side, shade a little bit. That's going to represent what we got. Let's obtain a p-value. Let's make a decision, and we'll summarize out here to the side. P-value is, what does the output say? 0.006. 0.006, we are going to reject the null hypothesis at, well, they don't give me an alpha, so I'm going to use my own. Perfect. We have evidence to suggest a linear relationship between courtship and marriage. Oh, my handwriting is getting sloppy. Here we go. That's it right there. All right, construct and interpret confidence interval. Confidence interval, I'm thinking panic. I've already done the assumptions up here because it's the same data set. So let's get right into the interval calculation. The interval calculation is going to be the slope. What is the actual slope? Man, I have gone back too far. My bad. Here we go. 2.4559. Use the whole number. They gave it to you. 2.4559 plus or minus t lookup. We'll have to go do that. Times the standard error of the slope. Okay, going back here. Standard error of the slope, 0.6669. 0.6669. All right, t-value. So again, my sample size is 10, so my degree of freedom is 8. Remember, since it's bivariant data, subtract 2. So 95% at 8. Oh, so it's the exact same number again. 2.306. 2.306. It just happens to be the exact same degree of freedom, same confidence level. Okay. Let's put this in our calculator. Let's go 2.4559 plus parentheses 2.306 times 0.669. Oh, there's an extra 6 in there. Let me try that again. 69. Okay, so my upper bound is 3.99377. I'm going to leave it at that. I'm going to go second entry. I'm going to just change the plus sign to a minus sign in my calculator. and then I get 0.91803. Conclusion: we are 95% confident the interval 0.9 to 3.99 captures the true slope. That's not how you spell slope. True slope between courtship time and marriage time. There it is. Panic on top of a phantoms. Know how to read these graphs they give you. Know how to get this computer output, right? Also, know how to get the least squares regression line. Y equals 5.710 plus 2.4559 if needed, right? Oop, X. There you go. All right. That is doing the problems with you.